So today we will look at the next kind of control source. We have finished looking at the voltage controlled voltage source and the voltage controlled current source. So today is the third kind of control source, and this control source has a lot of applications. So but it's actually a very easy kind of circuit. So this is the current controlled current source. Right, and this will give us the common gate amplifier, which we already hinted to yesterday. Okay. So, what is the property of a current controlled current source? What should its R in be, and what should its R out be? What should R in be for a current source? Infinite. Well, only two answers. If it's not one, it's the other. It should be 0. Right? We already have discussed this. And what should R out be? Infinite. Okay. So that's what we want to make. Alright. So if we want to make this, again, verbalize how you would do this. I have an input. So basically, current control current source. I want this. And let me also say that I want gain of 1. So that it simplifies matters, gain of unity. Okay, which means what is the kind of circuit we are looking for? The two-port representation of this circuit. The two-port representation basically would be that this is some current I1, correct, and I need to have a current source, correct, and the current source should be what? It should just be I1 itself, and so this is essentially what we are looking for, correct? So that if I were to excite this, which say, why would you want this kind of a current controlled current source with R in equal to 0 and R out equal to infinity? What would be its use? It will work as a current buffer. How will it work as a current buffer? So say I have some kind of source, right, which is some I in, and say this is a poor quality current source. What is a poor quality current source? It has some resistance. So it has some RS associated with the poor quality nature of this current source, correct? And then I feed this in here, and what will I get? Right? And then I put a load here, correct? So what is the current flowing through the load? So am I correct with the way in which I put the arrow here? Should I put it this way or that way? Which is better? This is better, right? Doesn't really matter, there will be a minus sign, okay, but this is a better thing because basically I want, so suppose RS were not there, then you connect this load, some RL, right? Suppose RS were not there, the connection would be just I in driving the load, correct? Now because you have an RS, all of this I in will not go into the load. What will happen? Some of the I in will go into the load, some of the I minus I in will go into RL, right? We don't want this kind of situation, so we use a current buffer. So what will the current buffer do? because the input impedance of this buffer, looking in here, right, your R in is 0, right. So what will happen to the current? Will any current flow through RS? Why? Because your Rn is 0, right. So all the current will go in through here, and this current source is intelligent. It will pump the same value of current into the RL, and because you have said that the output resistance of this current source is infinite, all the current will flow into RL. Correct? So this do you understand the operation of this as a buffer? And where is your R out? That is your R out. Okay, this is the connection without the buffer. Did I say current through RS is 0? If I said that is wrong. Thank you. Current through, current through RS will be 0, because okay, over here work out In is here. What is the current? So if I call this as say I alpha and this as say I beta, can you tell me what I beta is and what I alpha is? Okay, which one is which? Alpha first. Okay, we'll ask Nikhil, we'll ask Sai Kiran at the back. What is I alpha for this circuit? There are only two values of resistance, RS and RL. So tell me in terms of RS and RL. Vivek? R out is infinity. Thank you. R out is infinity. Yes. Okay. So now in this particular case, I alpha is nothing but RL by RS plus RL In. Correct? I beta is RS by RS plus RL into In. So if you have a non-infinite RS, then there is always going to be some current that is going as I alpha. Connecting it like this using the current buffer will allow you to pump In directly into the load. Correct? That's what we want. Okay. Any questions? Now, how do you go about doing this? Basically, I have, what do I have? I have my MOSFET, which is a voltage controlled current source kind of entity. And so I basically have the MOSFET, right? And I have a current source, right? So that is, let me say that I have my I in. So let me say this is my I in. Okay, and on top I am going to have my MOSFET. Okay, for simplicity we'll put I in pointing down. Okay, you can work out the actual direction based on the circuit. It's not really, but if I put it pointing down, I can explain it easier. So we'll assume that I in is pointing down. Okay, and on top I am going to have my controlled element. So as we had earlier, right, I am drawing only the incremental picture, because I in is an incremental quantity. We have already done such kind of circuits with quiescent quantities. When we were looking at how to bias the circuit, we looked at the situation where we took two current sources and those two current sources fighting with each other, right? Okay. Now when I mean this quantity above, when I mean this element above, right, it's a current source whose value can be controlled. I am actually alluding to the MOSFET, which is a voltage controlled current source. Okay, so we'll come there. Now what will happen to say this particular voltage here? Let me call that Vx. Okay, let me call this is I in, and let me call that as I out. I want to compare I out and I in, right? I ref was in the quiescent circuit. We don't have, that is not there in this particular. When we are looking at the incremental picture, the quiescent quantity does not enter. Okay, we will put in the quiescent quantity. Where will we put the quiescent quantity? When we look at the full circuit. First we will do the incremental circuit. Okay, what will happen to this Vx? Okay, let us look at this systematically. Firstly, you need to remember that this Vx is just not a floating node. There is some kind of parasitic capacitance sitting at this node, some C parasitic. Okay, if you don't include this, you will not be able to justify to yourself how this works. So there is some C parasitic sitting there. All right. Now let me assume for a moment that this connection is actually broken. Okay, assume that this connection is broken. What will be the value over here? What will this voltage be? This is, remember, this is the incremental circuit. So in an incremental circuit, what will this value be? It will be 0. Why will it be 0? No, don't assume that the parasitic has got shorted out. Because you are looking at an incremental circuit, you cannot have any DC values floating around, right? So that's why you don't have the DC value. Okay. Have you got that aspect of what I am trying to tell you? What I am saying is, this parasitic capacitance is just some parasitic in the circuit. Okay. Take any circuit. You have some, I have some circuit, right? So now I am drawing some full circuit here. So which amplifier do you like? Let's draw common source. Okay. So I have RA, RB, and then I have some load, right? And then what do I have here? Say I have some current source to set the bias and all of that, right? And I have some capacitor, and then I have my load, right? And then I have capacitor source. Okay. If I ask the question as to what is the voltage across any capacitor in the incremental circuit, right? That is, if you do not have any other thing, right? What would be the voltage across this capacitor, for example? What is this voltage in the incremental circuit? What is the voltage in the incremental circuit? 0, right? That's how we designed it, right? We want, in the incremental circuit, we want this capacitor to behave like a short. So you actually want this answer to be 0. Okay. So, okay, that's just an aside to keep it in mind when we do something. For now, you assume they are ideal. That's why I want to connect that's why I need to connect a capacitor there, or at least think that there is a capacitor involved, right? So this is just an aside, and the conclusion of this aside was what? Incremental voltage across capacitor is 0. Okay, so you keep that thing in mind, and now let us connect this thing back. All right. Now, if now we have done this many times, what will happen to Vx if I out is greater than I in? Vx will increase. Remember, these are incremental quantities. What will happen if I out is less than I in? Vx will decrease. Correct? Now, what will happen if I out is equal to I in? What will be Vx? Good. Right? So, that's why I described this circuit to you, the incremental picture to you. See, when we were doing the bias point operation, if you had the two currents equal, you really cannot tell me what is the voltage across the capacitor. It will be some value, but it will not change in time. Correct? Over here, because we are looking only at the incremental quantity, effectively is if you have these two current sources, it is equivalent to those two current sources being removed from this parasitic capacitor, right? So, and we already have discussed that in the incremental circuit, the voltage across the capacitors are 0. So, you will have Vx being equal to 0. Okay. So, that is important to remember. Okay. Now, with that in mind, can you think of a circuit that will actually do what we want? So, we have this, and I already told you, as we have done many times, that whatever I have in this box here is effectively going to become that's going to become the MOSFET, correct? The blue box is going to become the MOSFET. So, how will you draw it? So, if it's the MOSFET, and we are looking at the incremental circuit, this is essentially going to be that voltage control current source element, right? That is, you are going to have this thing like this, right? This will be some GM times some VDS, no, GM times VGS. Okay. Now, so which should be a source, which should be gate, which should be drain? This looks good to be a source. This should be the drain. Okay. And where is the gate? Gate is somewhere. That is your gate. That is my blue box. Okay. Now can you tell me, so I am going to have my I in connected here, and that capacitor which is there, we will now forget about it. It's done its job. Okay. What is going to be Vs when I out? So this is going, and how is I out going to be? Where is I out? So basically, to complete that circuit, right? This blue box is this blue entity. To complete the circuit, I have to put that, and then my I out is essentially the current flowing in through there. Okay, so you have I out and I in. When I out is equal to I in, what is the value of Vx, which is now Vs? 0. Okay, so what should you do? Will this work? So I have told you what Vs should be when I out is equal to I in. This controlling element is Gm into Vgs. Is there any other connection? The device is in saturation. That's why we are able to draw this equivalent circuit. Assume the saturation we will take care when we draw the bias circuit. My question is there something I should do to the gate? What should Vg? What should Vg be? I in by Gm. Okay. Think carefully. So what is happening to Vs? Okay, now let us write out the expression for I out. What is I out? Gm times Vgs, which is nothing but Vg minus Vs. Okay, and you know that when I out is equal to I in, your Vs is equal to 0. So what should Vg be? No, I out should be that, but this is a feedback loop. So this is when the system is in feedback, Vs will become equal to 0. So what should you put your reference to Vg at? No, you're still not getting it. Think. So assume that your Gm is also very large. So if Gm is very large, what's it going to do? If Vg minus Vs is a small quantity positive, then Gm very large into that will make a big change in your I out. and if Vg minus Vs is a small quantity negative, then I out will decrease by a very large quantity, and so when this feedback loop operates, Vg will become equal to Vs, correct? That's the only way you can have a finite value of current flowing. If you have Gm being infinite, then Vg minus Vs must tend to 0. This is essentially like your op amp. So what should Vg be? 0, right? That's all I wanted. So in the incremental circuit, I want my Vg to be 0. Okay, so that becomes the incremental circuit of. Has everyone got this? No? Okay. Because so as I said here, this is a current controlled current source for signals. So I am trying to make a buffer for a current source. So just as I have, for example, a microphone which is giving me a voltage, I can have, say, a photodiode whose output is actually a current. Okay, you bias the diode at a certain voltage, based on the amount of current, light that is falling, the amount of current will change. So the current is your signal. You want to buffer that current. So what I am drawing here is an incremental current source. Just as you had incremental voltage source, you can have incremental current source also, right? There is no problem. So these are all incremental quantities that I am drawing. So happens that the incremental quantity is a current source. Okay. All right. Now, so this is the incremental circuit of what kind of amplifier? Why do you call it common gate? Huh? In the common source amplifier, why did we call it the common source amplifier? Source was connected to ground. In the common drain amplifier, drain was connected to ground. Okay, over here, gate is connected to ground. So what about the situation that the drain is also connected to ground? No, this is a final circuit. So essentially, as I said, this is a current controlled current source, which means I can in principle also introduce some kind of load over here. It does not matter. I can put some RL here. What I am interested in is only the current through the load. Correct? So the moment I introduce an RL, my drain is no longer connected to ground. However, gate will have to be connected to ground because that's how this thing is operating. Okay. Alright, now to clarify the question that all of you asked as to how this feedback is operating, we'll just go and do a brief segue into some feedback stuff. Okay. Let me take, let's do this is just some aside into feedback. Anyway, we need this for later, so it's good to do it now. Okay. So, let me have, for example, some amplifier block. Okay. Let its gain be A. Let me have some input. Let me call that some quantity. So, let me not say V or I, because that will pollute your mind and make you think only in terms of some either voltage or current. So let me say that this is some X, so that it is some general input X. Okay, X could be current, voltage. It could also be, if you are working in with mechanical systems, it could be a position, right? If you are working with some acoustic systems, it could be sound, anything, right? So it's an input. All right. Now, can someone tell me how this feedback thing works? So I take X and then I feed X in here, right? I have not put something here because I am going to put some block there. If I say that some quantity here, let me call that as XE. Okay. If there is some XE going into the block A, what is my output? A times XE. I take that A times XE, take it to a feedback block B, correct? What is the value here? AB XE, right? So if I have XE there, then AXE is here, and then ABXE is there. And what do I do with this? So I have to take this, and now I want to compare this quantity with X in. So I put a summing junction there, wherein I take X in at the positive input and I take this quantity ABXE at the negative input, and then I close this. Okay. Now can you work out what is the whole thing? What is the output of this particular circuit? Okay, let us work this out. Okay. What is XE now? It will be X in minus AB XE, correct? So now just solve this. So just take it this side. So XE into 1 plus AB is equal to X in, which means your XE is X in divided by 1 plus AB. Okay. Now there is some terminology here, and let me not confuse the terminology. So let me get that correct. Your X out. Okay. This quantity is also X out is here. Okay, X out is your A times XE. So what is your X out now going to be? Okay, this kind of expression will now be very, very familiar to you, right? This form of the expression, it will be A times XE, which is nothing but A X in divided by 1 plus AB. Okay, in things like this, what did you try and do? So what is the typical thing you did when you had a 1 plus GMRL kind of stuff? What did you do? Right, you assumed that AB is greater than 1, which implies what will happen to X out? Will become X in divided by B. Okay. Now let's give some names and explain what is happening. So this quantity, so if you take the ratio of X out by X in, X out by X in, what is the ratio X out by X in? No, A by 1 plus AB. This quantity is called the loop gain. Why is it called the loop gain? Because you go through the loop and you get, this is called the closed loop gain. Because when the loop is closed, your X out by X in is this. Okay. The quantity A times B. What is A times B? Can you give me a name? Okay. So A times B is called the loop gain. So this always confuses people. So because if you go in this loop, okay, you break the loop, right? You, for example, just open the loop here. You have taken XC here. You have gone through A. You have gone through B. What do you get? AB. So the output of just these two blocks is nothing but A times B. So that is your loop gain. Okay. Let's connect it back there. All right. Now, what are the advantages of this? Let's do some simple calculation. Okay. Let me assume that my A into B. Let me assume A into B is say 1000. Okay. Then what is your X out by X in? 1. So you don't know what is this, right? So one way of writing this is that you can write this closed loop gain as 1 by B, AB by 1 plus AB. Okay, so your closed loop gain is nothing but 1 by B into loop gain divided by 1 plus loop gain. Okay, so now if AB is 1000, what is X out by X in? 1 by B into? That's what I want, 1000 by 1001. Okay, now assume your A into B is, instead of 1000, let me assume it is 10,000. What is your X out by X in? 1 by B into 10,000 divided by 10,001. Okay, work out what these two things are. That's okay. Work out. Who has a calculator? Tell me what's the first number, what's the second number. This is 0.999 divided by B. And what is this one? Okay, this is 4 nines divided by B. Okay, so what is the difference in these two quantities? So I call this as X out by X in 1, and this is X out by X in 2. Okay, so what is the ratio of this X out by X in 1 divided by X out by X in 2? That will be how much? So it will nothing. It will be 0.999 divided by 9999. Work out what this is. Actually, work it out in terms of the other numbers. That is, work it out as 0.999 is 1000 by 1001, and this guy is nothing but 10,000 by 10,001. And tell me what this is. Who has backbench somebody with calculator has to give me this number. So it's effectively 0.9999 something, right? So this is approximately 1. But what is the change in your AB by A? So what is happening here? So you can assume, you assume B is fixed, A changes, right? So for a change in A of how much? 10x. What is the change in your X out by X in? No change. Right? So this is feedback in operation, no? So you can have your amplifier A whose gain can change wildly. As long as it is large, the gain is effectively set by B. And what is B typically? I am talking of gain, and then your answer is having a 1 by B. So what is B? Usually what kind of network is B? No, what? So A is your amplifier, I have said. So what is B then? Is the feedback element, and the feedback element is typically some kind of passive element whose properties you can fix. So for example, one typical B element is this. Right? If I have R2 and R1, then your B is, what is B? R1 by R1 plus R2. That's your B. Okay. So that's why wherever you are having this, right, you are having your answers as 1 by B. So when you take, so B is less than 1. So 1 by B will actually be a gain. So you will still get a gain, but it will be much less than value of A. All right. Why did we do all of this? To understand what is XE. So what is XE when AB is much greater than 1? Huh? Yeah, but there is X in by AB, and what can you say about this? This tends to 0. Right? So when the feedback loop is operating, what is happening? It is comparing X in and this X out, right? It's actually comparing X in and X out times B and ensuring that both of them are equal. And when both of them are equal, this XE tends to 0, and that's why the name XE, because this XE is called the error signal. Right? XE is the error. Right? So what this tells you is, if you have a gain, if you have an element with high gain, then the input side you can have a very low difference between the two quantities, or basically the input can be very low, and that's exactly what is happening in the previous case. Right? When this system is operating in feedback, the small change in your Vg minus Vs, now Vg minus Vs is your error signal, so even a small change in your Vg minus Vs ensures that your I out corrects itself. Okay. So now let us analyze this circuit and see where that feedback actually is operating. Okay. How do you think, where do you think that will operate? Right, there is something which we have to do, right? So we will do that. Okay. All right, we will continue with this in the next class. Think about this.